In order to think about how glaciers flow, we need to come up with a good physics-based framework for describing the process of ice deformation. There's a whole field of physics that's devoted to the deformation of continuous materials. It's called continuum mechanics. And the goal of this video is to bring up some of the basic concepts of continuum mechanics so that we have a vocabulary that we can use to understand glacier flow. The primary terms we're interested in defining here in this presentation are stress and strain. You'll remember from your high school physics concepts of force. So Newton's second law says force equals mass times acceleration. Forces were these things that could put bodies into motion, these kind of discrete objects. If you apply a force to them, their tendency is to accelerate. In continuum mechanics, we're not focused on a discrete body with a force applied. Instead, we're interested in the mechanical material of materials that are kind of a continuous mass. And these continuous masses, instead of accelerating, we think of them as deforming, changing shape. So, forces, in order to get to a force, we can think about Newton's second law and build up the units of force. The units of mass we know are kilograms. Acceleration maybe doesn't immediately have units in your mind. Distance traveled is in meters. The velocity that something's moving, its speed is usually in meters per second. The rate that the speed changes is in meters per second squared. This is our acceleration. So, mass times acceleration is force. Force, therefore, is kilogram meters per second squared, has the unit of the Newton. Stress is an interesting reframing of the concept of force for these continuous materials. If we imagine that we have a block, maybe a block of ice, we can imagine two different types of forces that act on this block of ice. The first is something we call a body force. A body force acts everywhere within the object. For example, gravity is a body force. Gravity is pulling on every single individual component of this object. It is also possible for there to be forces that only act on the surfaces. Imagine, for example, I tied a string to this plate that is the edge of our box, and we pull on that plate with a particular force. That force isn't acting on everything, it's just acting on the surface. And that force is distributed over a finite area. We call this a surface force, or often described in terms of stresses. And these stresses have units of force per unit area, newtons per meter squared. Okay, so stresses are forces applied to a surface, therefore distributed over an area. If you think about, for example, the stress that you apply to the ground when you're standing, you can take your body weight, divide it by the size of your feet. That's the stress that you're applying to the ground. When materials deform, we can come up with a way of describing their deformation mathematically. And the term we use to describe deformation is strain. Strain quantifies the deformation of a material. Stresses result in strains. So this is our force per unit area that acts to deform a material. Let's start by thinking about a one-dimensional material. So think about like a guitar string, for example. Here's our guitar string. We can apply a stress to the ends of this guitar string. We can pull on it. Or actually, let's think about a rubber band. We can apply a stress, pull on that rubber band, and change its length. Say it started with a particular length. When we pull on it, maybe it gets a little bit longer. We'll call that delta L, the extension of that rubber band. Strain is equal to the change in length over the length itself. As a result, strain is a dimensionless quantity. It has no units. Its numerator had units of meters, its denominator had units of meters. That leaves us with something with no units. Thinking about the relationship between the applied stress and the strain leads to things we call constitutive relationships. They describe how a material deforms when you apply a stress. The constitutive relationship for a rubber band, or for a spring generally, is called Hooke's law. Hooke's law says that when you apply a force, a spring will change length scaled by something called the spring constant, some constant value. You apply a stronger force, it will be a more deformed material. A lesser force, it will be a less deformed material. These relationships that say the stress is proportional to the strain, this is what we call an elastic material. As you increase force linearly, your strain also increases linearly. So here's our concept for one-dimensional stress and strain. You apply a force to this surface that is the edge of the wire, the rubber band. You pull, it leads to a deformation. We can expand this concept of stress and strain to more than just one dimension. So imagine we have a box. And let's say we tied a string to this surface of the box and we pulled the string in that direction. Now, to think about how the object will deform, instead of just, pulling along a single dimension, now we have these two dimensions we have to work with. We can decompose that surface stress, that as what we actually call a tension force. We can decompose it into two components. A component that's perpendicular to the face and a component that's parallel to the face. If we have, for example, this tension force, maybe we can define those two components using some useful nomenclature. To do that, we have to define some axes to our two-dimensional system. Here's x, here's y. Y. We're going to define these faces. These will be the x faces, because it's the face that is perpendicular to the x-axis, or normal to the x-axis. These will be the y faces. So, both of these stresses are acting on the x face. So we're going to start with a little sigma x to describe them. But this stress is acting in the x direction, while this stress is acting in the y direction. So now we have some nomenclature. We can have a stress xx, stress xy, where stress xx is acting to stretch the box. Stress xy is acting to what we call shear the box. We call this a normal stress. We call this a shear stress. We might similarly have some pull on the y face that we can resolve into a sigma yx and a sigma yy, where this again is a normal stress, this is a shear stress. This collection of four numbers can tell us about all of the stresses being applied to the box. So our normal stresses, they're trying to change our box to look something like that, to stretch it. Or maybe to look something like this, to stretch it this way. Sigma xx might make our box stretch this way, sigma yy may make our box stretch that way. The shear stresses are taking our box and they're turning them or trying to deform them into something like that. We call that style of deformation shear strain. So, in the case of our normal stresses, we can think about, our normal strain, we can think about them with the same definition that we used in one dimension. Normal strains are just our change in length divided by our length. We might, for example, use the term right here that describes strain from the x face in the x direction, this stretching. In addition, we can have a strain associated with shearing. This strain describes the change in length in the x direction divided by the initial length in the y direction. So in this case, here's our delta L. Our shear strain here would be equal to delta L over L. It's possible to set up a constitutive relation for each of these stresses and strains. If we had an elastic box, then it's likely the case that sigma xx is proportional to the strain in the xx direction. Sigma xy is proportional to the strain in the xy direction. Sigma yx, the strain in the yx. Sigma yy, strain in the yy. Convention is that the first subscript describes the face on which our stress is acting. The second describes the direction in which our stress is acting. One other important convention is that normal stresses tend to be positive in tension. So if you're pulling something apart, the stress is considered a positive. If you're in compression, the stress is considered a negative. Okay, the last thing to think about is that we can extend our definition of stress and strain to as many dimensions as we want. So we can have something pulling on this face of the box, which we can resolve into a component in that direction, a component in that direction, and a component in that direction. Now we have two shear stresses. We can think about this as sigma xx is here. Hang on, let me define a coordinate system. Here's x, here's y, here's z. So remember, this first tells us which face we're acting on, which is this face here. The second tells us the direction that we're acting. We can also have sigma xy, so acting on the x face in the y direction. And here we have acting on the x face in the z direction. So we can come up with a full, what we call a stress tensor, that describes all of the applied stresses, where these are our normal stresses and these are our shear stresses for our three-dimensional object. The last thing I want to define for you is an idea of rheology. So we talked about a constitutive relation. Elastic materials, the strain is proportional to the stress. If you apply a fixed stress, the body will change its shape and then stay at its changed shape until you release that stress, and then it will go back to its original shape. So here we have these elastic rheologies, where when you apply a stress, you have deformation that is proportional. An interesting thing about elastic materials is that deformation is also recoverable. That is, when you release the stress, it will go back to its original shape. Fluids don't behave this way, and we often use the term viscous to describe how fluids deform. So instead of stress being proportional to strain, which is the case of elastic materials, when there's an applied stress on a fluid, that leads to a deformation that continues to occur until the stress is relieved. And in fact, the stress isn't proportional to the strain, but it's proportional to the strain rate, the rate at which something deforms. Remember that the units of strain were unitless. Units of strain rate is 1 over seconds. So, if we imagine our rubber band, for example, if we change its length by 20% in 1 second, then its strain rate would be 0.2. Because if we increased its length by 20%, the strain would be 0.2 over 1. And we said we did that in 1 second, so the strain rate would be 0.2 per second. For viscous materials, the strain rate is proportional to the stress. So if you have an applied stress, every second that material would get longer by 20%. Another second passes, another 20%. Another second passes, another 20%. Viscous materials continue to deform at a constant rate given the applied stress until the stress is relieved. And when the stress is relieved, it doesn't return to its original state. It simply stops deforming. That's an interesting distinction. So we have elastic materials, we have viscous materials. When we think about the ice flow problem, elastic strain does occur in glacier systems. It's what allows seismic waves to propagate through glacial ice. But we typically aren't interested in elastic processes. We are interested in viscous processes. So the rate at which ice deforms, much like a fluid, scales with the applied stress. Within glacier problems, we have a couple of different styles of viscous behavior. We have something called linear viscous behavior, which is to say that the strain rate is proportional to the stress. In this case, tau refers to a shear stress. Sometimes we call these Newtonian fluids, where the viscosity relates the stress and the strain rate. We also have some systems where the strain rate is proportional to the stress to some power. These power law fluids, sometimes called non-Newtonian fluids, behave in some interesting, unique ways. Ice is a non-Newtonian fluid. It deforms according to this strain rate equals a tau to the third. We also have some materials that don't deform at all, subject to some stresses. You keep pushing, you keep pushing, you keep pushing, and eventually they deform catastrophically as soon as you reach a particular stress. We call those materials plastic. They don't deform at all for many stresses until you reach what's called the yield strength, the strength at which they'll deform, and then they deform like gangbusters. So, to think about ice flow and the processes that drive ice flow, which involve the deformation of ice, it involves the resolution of stresses at the base of the ice, at the interface between ice and rock. We need to be able to think about stress and strain rate, and we need to understand what those terms mean. Remember, stress is force per unit area. It can act parallel to or perpendicular to the face of an object. Strain rate or strain is the deformation of that object. You can either shrink it, change its volume, or shear it. So with that, we can start to get into some of the details of the physics of ice flow.